Is collapse of the Atlantic Ocean circulation really imminent? Looking at the history of icebergs may be able to ascertain some clues as to this question. Hello friends, Jim here. So there's been a lot of talk recently about AMOC collapsing and the Gulf Stream collapsing, etc., etc. Well, first of all, the Gulf Stream is not going to collapse for reasons I will explain later on. And we'll take a look at this diagram later on. So let's see what they're saying here. So people now, I think people are starting to understand that climate change is here and is already impacting us, impacting our daily lives. And of course, when you get Hollywood movies, that heap on the fear and so forth, such as The Day After Tomorrow, which it was entertaining, but they took a smidgen of a concept and used that and ran with it to make a movie. So, I would not take it as settled science. Let me put it that way. Okay, and Hollywood does take a bit of liberties with how things happen, but there are questions about, of course, AMOC, the Atlantic Meridional Overturn Circulation, and it is important because specifically speaking, it's the North Atlantic Drift, which is a branch off the North Atlantic Gyre. It is this branch that brings the heat and nutrients and milder conditions to places such as Iceland, the Scandinavia countries, the UK, Northern Europe. If that slows down, which is being measured, let's be clear about that, then we can expect to see, I postulate that we would expect to see cooler conditions in that section of the globe. So when that current, North Atlantic Drift, if that stops circulating heat to the higher latitudes, that changes the situation. And most recently, we saw this about more than 16,000 years ago. However, it relies on Greenland shedding a lot of ice into the ocean. Now, they're saying ice, not water. The big difference. And I'll explain that as we discussed in this video. New research published in the journal Science suggests that while Greenland is indeed losing huge and worrisome volumes of ice right now, that might not continue for long enough to shut down the current on its own. Looking at the evidence from the past explains why this may be. So the Atlantic current system distributes heat and nutrients on a global scale, the conveyor belt colloquially taken. And what happens is, as you know, for those of you who have been following my channel for some time, you take warm water from the tropics, you move it northward, goes up the U.S. Atlantic coast, crosses over the Atlantic, which is the North Atlantic current, different from the North Atlantic Drift. As some of that warm water evaporates and the surface water cools, it becomes saltier and denser. Of course, the dense water sinks, and as colder, denser water circulates back south at depth. Variations in heat and salinity fuel this circulatory system called thermohaline flow. Were the Atlantic circulation system weakened, it could lead to climate disruption. Ice sheets, of course, are basically frozen water. So any rapid release of icebergs into the Atlantic Ocean can lower the ocean's salinity and slow down the deep water formation. If the surface water is no longer able to sink deep and the circulation collapses, dramatic cooling would likely occur across Europe and North America. Both the Amazon rainforest and the Africa's Sahel region would become drier. Antarctic's warming and melting would accelerate, and this could take place on the order of decades. Now, a little caveat about all that. In the past, you had the slowdown collapse of AMOC. Ice sheets grew in the northern hemisphere. Had an ice age. Well, thanks to all that ocean heat, I am of the opinion now that you'll get regional cooling, such as I mentioned at the outset, Iceland, Scandinavia, the UK, Northern Europe. You're going to get regional cooling, but it would be insufficient for ice sheets to grow and expand and, move southwards. Today, the Greenland's ice sheet is melting rapidly. Some scientists worry that the Atlantic current system may be headed for a climate tipping point some point this century. So, are these fears founded? Let's take a look in the past. So, here's Greenland, and this graph shows the change in mass given in gigatons, and we're starting at 2002 up to 2023. So the even years are in gray, the odd years are in white. Let me see if I can enlarge this. There we go. So we can see here are the even years, these are the odd years, and you got some seasonal variations, but the clear trend is very clear. The average mass loss is 269 gigatons per year, right? Just run a slope through that. This is the ice mass change. So this is in meters water equivalent relative to 2002. So as expected, the great majority of the ice loss has been on the periphery. Basically, the very center, which is also where the highest elevations are, the very center is where we're seeing perhaps a little bit of ice accumulation, but for the great majority of the Greenland land mass, it's losing ice. You can see that clearly. Right? So this is going to be the last bit of Greenland that loses its ice if conditions continue as they are. So, in the 1980s, a junior scientist named Heinrich and his colleagues extracted a series of deep-sea sediment cores from the ocean floor to examine whether nuclear waste could be safely buried in the deep North Atlantic. Sediment cores are full of information, and basically it's accumulated information. You have deposition on the seafloor and it compacts down. You get a core and you've got a history of how far back it goes, depending on how deep of a core that you yanked out of the ground. What Heinrich found was several layers with lots of mineral grains and rock fragments from land. This is in the mid latitudes. The sediment grains were too large to have been carried to the middle of the ocean by wind or ocean currents alone. Heinrich realized that they must have been brought there by icebergs, which had picked up the rocks and minerals and the large sediment grains when the icebergs were still attached to the glaciers on land. So what happened was the icebergs calved off, they broke off, currents brought them to lower latitudes where they then melted and started to deposit the materials contained therein. So the layers with the most rock and mineral debris from a time when the icebergs must have come out in force coincided with severe weakening of the Atlantic current system. All right? The layers with the most rock and mineral debris from a time when the icebergs must have come out in force coincided with severe weakening of the Atlantic current system, and those periods are known as the Heinrich Events. Paleoclimate scientists use natural records such as sediment cores to ascertain what took place in the past, and then from that we try to extrapolate, project what future conditions might become. By using uranium isotopes in the sediments, we were able to determine the deposition rate of sediments dropped by icebergs. The amount of debris allowed us to estimate how much fresh water those icebergs added to the ocean and compare it with today to assess whether history might indeed repeat itself in the near future. So why a shutdown is not likely soon? So is the Atlantic current system headed for a climate tipping point because of Greenland melting? The authors, and let's mention their names here, that's Yuzhen Zhao and Jerry McManus, they do not think so. They think it's unlikely in the coming decades. While Greenland is losing huge volumes of ice right now, worryingly comparable to a mid-range Heinrich event, the ice loss will likely not continue for long enough to shut down the current on its own. Icebergs are much more effective at disrupting the current than meltwater from land because icebergs can carry fresh water directly out to the location where the current sinks. Further warming, however, will force the Greenland ice sheet to recede away from the coast too soon to deliver enough fresh water by iceberg. So in other words, what they are saying is as follows. If you get chunks of ice just breaking off and the currents bring them down south, when that melts, that can shut down the deep water formation. Meltwater alone, adding the freshwater land, while it does indeed slow down deep water formation, where what we call chimney formation and sinking rates do decrease, because there's fresh water, and the Atlantic Ocean is not exactly known to be in the calmest of oceans. There's a lot of mixing. So you can better disperse that fresh water horizontally as well as partly vertically. That's what they're saying. Now the strength of AMOC is projected to decline anywhere from 24 to 39% by 2100. By then, Greenland's iceberg formation will be closer to the weakest Heinrich events of the past. Heinrich events, in contrast, lasted 200 years or so. Instead of icebergs, meltwater pouring into the Atlantic at the island's edge is projected to become the leading cause of Greenland's thinning. Meltwater still sends fresh water into the ocean, as I just said, but it mixes with seawater and tends to move along the coast rather than directly freshening the open ocean as drifting icebergs do. This is an excellent synopsis, a summary of the difference between the two. And again, for those folks who are saying, well, the aerosol is causing AMOC to slow down, they need to take some oceanography classes, because at high latitudes, subpolar, polar region, right, which is where AMOC forms, ocean water density is determined by salinity, not temperature. In the tropics, yes, temperature is the driver of ocean water density. But we're not in the tropics. So, atmospheric folks, please take some oceanography classes. The future trajectory of the Atlantic current system will likely be determined by a combination of the decelerating but more effective iceberg and the accelerating but less influential surface runoff. This will be compounded by rising ocean surface temperatures that could further slow the current. But what is the source of the rising ocean surface temperatures? Ocean heat content, because sequestration to depth is slowing, so that heat starts to diffuse upwards. It gives rise to the increased sea surface temperatures. It continues to diffuse into the atmosphere, and then you fuel really nasty hurricanes. And usually when after a hurricane comes through, you have a resulting upwelling, and because it's sucked, in the past, it sucked up all the heat that was there in the surface waters, and then you get an upwelling of cool waters. That's not happening. Look what happened in the aftermath of Beryl. You still got hot upper layer ocean waters. It did not cool down. And that's because of ocean heat. So again, any light penetration from more sunlight reaching through is not going to impact all the way down to 100, 200, 300 meters. It just is not. It's going, because it attenuates quickly in the upper couple of meters, and that's assuming smooth surface, attenuates rapidly, exponential decay. To see ocean surface temperatures as high as we're seeing it is more than just simply a little bit of extra sunshine. It's due to ocean heat content that is upwelling. So that's what it is. So we can sum this up. Icebergs, when they break off, they get into the middle of the ocean and have more of a direct impact on whether deep water formation takes place. Freshwater melting of the ice, putting in freshwater lens, does slow it down, but then it gets constrained along the coast. There's some mixing. So even though there's going to be a slowdown, it's less likely to lead to a shutdown, as will the icebergs. So now let's take a look at this figure here. So this is today. The Gulf Stream is part of both horizontal subtropical gyra and the vertical AMOC. Okay, here's AMOC, warm water, illustrated in this orangey color. It sinks, as it cools, it sinks, indicated by blue, and flows back in the deep layers. So we'll start at 1 here. Warm surface current driven by winds and replenishing sinking. Okay. 2, water and heat transfer from the tropics to northern latitudes. Right. And then 3, close to the poles, water cooled, becomes heavier, sinks to the bottom. And 4, the cold deep water is exported southward. Okay, so here's the return flow from the conveyor belt, right? Gulf of Mexico, here's the Gulf Stream, right? Nice, and here's the Gulf Stream, westward intensification. This branch right here, follow the cursor. This branch right here is the North Atlantic Drift. A little branch going this way towards, Newfoundland, so forth. But here's the North Atlantic Drift. This branch here, that's the North Atlantic Current. So we got the North Atlantic Current, North Atlantic Drift. When people say the Gulf Stream is going to shut down, it's going to collapse, that is simply incorrect. As long as planet Earth is rotating and you've got all this liquid sloshing around, you're always going to have a gyra. Because you're always going to have temperature and pressure differential that's going to create winds. You're going to have a wind stress. So gyras result from wind stress creating pressure gradients that then you have to balance vorticity, you have to balance Coriolis, and you get a little circular circular flow going on. Right? So when the deep water forms, it returns this way. And here, see what they mean when it hugs the coast? So any freshwater entrainment is going to likely be pushed along the coast. And why is that? Because there actually is a little gyre right up here. And that little gyre rotates counterclockwise, so it brings the water this way. So the water comes up this way and gets pushed that way. And you got the surface flow here, so by conservation of volume, you have the underflow this way. And it returns. So that's today. In a warmer world, what happens? Climate change weakens AMOC. Slows the Gulf Stream, doesn't stop it. And presumably slows the Gulf Stream because the wind stress is reduced. So here's the AMOC. Here's the AMOC in a weaker state. Still going to get some deep water formation. You're still going to get the backflow. Waters become fresher and lighter, therefore sinks less, but you might still get some sinking. Much less heat and water are transferred. So you're going to get a cool down in these regions. The Gulf Stream weakens, but the portion pushed by winds remains. So it depends on the pressure gradients. And for that matter, the temperature gradients. Right? So you can still see the North Atlantic current, the North Atlantic drift. You can still see them. The Gulf Stream is not going to collapse. North Atlantic drift may slow or stop. And we have evidence that that has happened in the past. So that's really, kind of diagrammatically, but that's showing what goes on. So, again, I'm going to repeat myself, but to sum up, freshwater input will slow AMOC down as we're measuring it. It is unlikely to lead to a complete shutdown of the deep water formation. What this analysis indicates is that icebergs actually breaking off, as opposed to just melting away, but breaking off and getting into latitudes like around here, where it suddenly melts all that water. So you have a sudden melting of an input of fresh water that can lead to the shutdown of AMOC. And this is based on deposition of material, rocks, large sediments, called the Heinrich Events, and also looking at some uranium. And I did another video discussing this in a related topic where they looked at the thorium as well. You might want to check out that video as well. So that's kind of the essence of what they're saying. And what they're saying is, as you continue to melt the ice, right? As you continue to melt the ice and all this melts away, well, there's less ice that's likely to break off and get into the ocean. That soon all this ice will be gone and you're not going to get the icebergs. You just have continual freshwater input. That's the other thing they're saying. So interesting study, interesting hypothesis. If you wish to learn more of this topic that was discussed today, please support my work. You can do so by joining my YouTube community, become a patron at Patreon, or buy me a coffee. You'll see the details on the screen as well as in the description box. There I will do a deep dive video providing my analyses of the various figures as well as explanations of the concepts and their importance to the research that is featured. Thank you.